So this is the typical vision range for a regular eye or healthy eye, that a regular person's eye who doesn't have any eye problem can see stuffs as close as 25 centimeter to the eye without stressing our vision. Stressing our vision means that if you if some if an object is placed closer to 25 centimeter, uh, we can actually still see it, but to be able to see that, we have to really put some serious uh, pressure onto our optical systems, and we have to deliberately keep focusing our eye to that object every once in a while. So we have to put some additional attention towards focusing to that point. But if an object is placed at about 25 centimeter close to our eye, we don't have to do much effort. That location can be automatically focused by our eye muscles and suspensory ligaments. That's why we call the near point. Near point basically means the closest distance or the closest point at which the eye can see without any stressing the vision. And the far point is actually pretty much far away, like at infinite distance. Now, regular human eye, naked eye, can see up to infinite distance doesn't mean that it can see far objects, zoomed vision, nothing of that sort. It means far objects look unblurred. So if there are, let's say, dots in the sky, individually distinguishable dots, then healthy eye would be able to count how many dots are there. That much is good. Those dots are not gonna look like a blurred vision of cloud or something like that. So being able to see objects which are really far away doesn't mean that being able to have telescopic vision at a really far away distance. It means that really far away objects are still visible without their edges getting blurred or the unfocused. That's what a healthy eye does. Whenever this vision range becomes different than what it is, that's what we call a faulty eye, or eye that has some problem. So there are two types of problems that we can have. We can have short-sighted problem, which is called myopia. That is a doctor name, or in the physiological name of the problem. Or we can have a long sight problem, which is hypermetropia. The idea is very simple. I'm going to draw it up over here. If some eyes physical vision range gets closer, let's say there happens to be an eye that can see without any goggles or without any spectacles, the near point gets closer and the far point gets here. So if an eye is such that it can only see objects within this range, so I'm drawing it up over here. So I should actually draw it up over here. As I draw it up over here. If the vision range of a certain eye gets closer than the actual normal eye vision range, let's say something of this sort, this is the problem that we call nearsighted problem. So this is near sight. So basically the whole range is getting near to eye, we call it nearsighted. On the other hand, if some eye has some problem that the whole vision range gets really farther away, which means the near point gets farther away, but it doesn't, but the far point was being at the infinite distance, pretty much remains at the infinite distance. So that's not, there is no far away from over here. So that is what we call a far sight. So these are the two different type of problems, and that's how we name them. Now the idea is that what could possibly happen, or why should we have this kind of problems in the first place? So to understand that, we first have to understand how does the eye work. Our eye works by some circular muscles which are called ciliary muscles. You don't have to know that for physics, but for those who have biology, you might as well know that those things can squash up the lens to make it thicker, at which point it gets a much smaller focal length, or it can magnify, it can convert the light rays more, and the suspensory ligaments can pull away the eye lens at a certain amount so that it can actually become thinner. The balance of these two opposite effects basically gives us our eye a very fixed type of required focal length. I'm using the word required focal length because the way a human eye looks is something like this. Let me use green maybe. Let's say this is the shape of the eyeball. In front is a bit of a dent, which is the cornea part, and over here we have the lens. The lens is less curved in the front and more curved at the back. That's how human eye is about. It's not equally curved on both sides, but for simplicity's case, you might as well see equally curved eye lens in many drawings. No big deal. For a specific eye, for any eye, human eye, this distance is always fixed. This is the distance that we call image distance from the optical center of the lens all the way to the retina. This is a fixed distance. So if we want to see objects which are at different distances away from the eye, we have to somehow be able to merge all the light rays. Let's say this is the near point of the eye. So let's say this is the near point and it goes on further. So if light rays are coming from here, a healthy eye should be able to converge them such that the light rays actually gets merged exactly on the retina. So their crossing should be exactly on the retina so that we have a fine image or crisp image or clear image, something that is called non-blurred. We call it proper vision. And even and so this is going to happen. And the way a healthy eye works is that when the object is pretty far away, for example, over here, over here, over here, really far away distance, no matter where the light rays are coming from, a healthy eye is capable to converge all of those light rays onto the same spot of the retina. Okay. So onto the retina. That's how the eye works. And the way it works is by effectively changing the focal length or the magnification capability of the eye lens. So that's what changes. The image distance always remains the same, but the object distance can vary. Now, healthy eye can effectively handle all the light rays that comes from the near point all the way to the far away distance. What happens to short-sighted eye is that it can happen in two different ways. So I'm going to write over here short sight. Either if the magnifying power, I'm not going to use magnifying. What I'm going to I'm going to write that eye lens. Where's my box? So these are the two physical reasons for which short-sighted can be developed. Eye lens can become too powerful, or the eye size can become bigger. So this is the part that I want you to understand. Let's say this is a healthy eye. I'm going to use this figure to explain short-sightedness, and then I'm going to, for the long-sightedness, I'm going to draw another figure. Try to understand. All the green lines that you can see, are the actual light rays that's going to happen for a healthy eye. So even if an object is over here, let me erase this part. Maybe I don't need that. The light rays are going to be focused on the back of the lens, and also if we have light rays coming from a really far away object, let's say from infinite distance, so I might as well try to draw parallel light rays. Let's say I'm going to draw that with green as well. So about parallel light rays, representing light rays coming from a really far away point, they are going to be also marching onto the retina as well. That's how the healthy eye works. So all the green things are for the healthy eye. Now showing for the short-sighted with red. So the way short-sighted eye works is that it can have a bit of a more magnifying power than what it should have, which means whenever light rays from infinite distance comes by, it magnifies them or it converges them more than it should. So as a result, those light rays can actually cross each other before they meet onto the retina, and actually can have a physical cross point in front of the retina. So the image is not actually created exactly at the retina, it is created in front of the retina, and so the retina actually gets a more of a blurred image. So this is happening because healthy eye was supposed to convert the light rays less, so that the merging of the two light rays should happen exactly on the retina, but the problematic eye short-sighted eye doesn't do that. It converges them more, so it crosses over here. That can be problem number one. That is a possibility. The other possibility is I wrote and/or. It means either of these problems can cause short-sightedness individually, or a person can have both of these problems happening simultaneously. It's going to give them a really significant problem of short-sightedness, but together they can also cause the same effect. the eye size or the image distance gets bigger. What this means is that, let's say this was the supposed to, so for this example, consider that the red lines don't exist. So let's say the red lines don't exist. Just consider that the red lines don't exist. Let's say the green shape was the original shape of the eye. Let's say the lens is still working okay. So light rays are still following the green lines over here. But for some medical reason, for some problem of the eye, let's say the eyeball size got a little bit bigger. So the retina, which was supposed to be right over here, has now reached up over here. So what is happening? Now the light rays are pretty much getting converged by the same amount by the lens. Lens is doing its job right, but the location where the retina was supposed to be, the retina has gone further behind. So that's the problem. Does it make sense? One.
Yes, sir.
Okay. So that's what happens for light rays coming from infinite distance, and it actually gives an eye a little bit of advantage for the case of the nearsightedness, is that if the object, I mean, healthy eye usually can see the objects which are placed at near point pretty easily, but for short-sighted eyes, if you place an object pretty close to the eye, let's say somewhere over here, the eye would still be able to converge them perfectly onto the retina. So that can also work, which means the near point gets further close, and and if we slowly start to move the object further, there is a certain physical point beyond which everything starts to look blurred. So the eye can comfortably see a short distance close to itself. So far objects seem to be blurred, and that's what we mean by short-sightedness. So how do we take care of it? The idea is very simple. To manage or to correct the problem, we have to cross the light rays a bit further away from the lens. So now the crossing of the light rays are happening in a position which is not at our retina. We need to have this crossing a bit further out, which means somehow we have to reduce the power of this lens. Now doing that biologically to can actually take a lot of time and a lot of adaptation for the human being. The simpler process is that we introduce a small, specifically measured concave lens or divergent lens in front of the eyes. The way this lens works is that whenever light rays are coming from infinite distance, there's a parallel light rays. These light rays become slightly divergent before they reach into the eye. Coming to the lens, they become slightly divergent before they fall into the lens. And as those divergent light rays actually fall onto the lens and eventually they are converged back, that additional amount of unnecessary convergence is actually counterbalanced, and as a result the light rays will then be perfectly onto the retina and that problem will be taken care of. So that's how it works. So that's basically the whole situation for the short-sightedness and its cure. Key points for you to remember is that short-sighted means the whole range of vision has become closer. Why that happens? Because light rays meet in front of the retina. Remember that. How could the light ray meet in front of the retina? By two possible reasons. Either the lens has become more powerful than it should be, so it's converging the light rays more than it should, or the eyeball has become bigger, or the image distance has become bigger. So the lens is doing its job right, but because the retina has gone farther away from where it should have been, the light rays are now crossing in front of the retina, so which is giving us this trouble. So this is the whole thing about the short-sightedness. What happens for long-sightedness? Let me just draw a healthy eye first, let's say. So let's say for an healthy eye, this is the near point and this is the faraway point. So light rays coming from the near point fall perfectly onto the retina, and light rays coming from infinite distance, which are somewhat parallel, almost parallel, would also fall onto the retina. So that's what happens for a healthy eye. And what happens for a long-sighted eye? The idea is very simple, as the name says, and I showed you a bit earlier. Long-sighted eye or the problem is called long sight. The eye is called long-sighted eye, using that noun as an adjective. So for a long-sighted eye, the problem is just the opposite. What happens for long-sighted eye? For some sort of problem development, the light rays which are supposed to meet at the retina are going to meet behind the retina, which means it will be happening for exactly opposite reasons as over here. Eye lens would be losing power, or it would be, or the f would become bigger. So light rays would meet behind the retina, or maybe the eye size has become smaller. So the lens is doing its job right, but the image observation, the retina has got a bit closer to the lens. That's why the placement is not working well. So the problem that happens for a long-sighted eye that it cannot see objects close to the eye. So its near point goes further out, which means whenever light rays comes from the near point, this is the actual, this is supposed to be the near point, which is about 25 centimeter from the eye. Light rays coming off from this point falls onto the eye, and then it tends to meet behind the eye. So you can see that I have drawn the light rays up to the retina with solid line and drawing the remaining part with dotted line, because obviously the light rays are not penetrating through the retina to and going through the skull to meet behind it. It's just a hypothetical crossing point representing that the light rays are attempting to meet behind the retina. So that's why I use the dotted line. So that's the problem that happens. So how can we, I mean, what is the essential remedy for this? I shouldn't use remedy. What is the essential, I mean, from which point should the eye be able to see clearly? That is very simple. If you slowly start to take the object far away from the retina, the light rays which would be falling onto the eye would become less divergent. The farther it is, the less divergent the light rays are going to be, and this point is going to get closer. You should remember from our earlier class that whenever we take the object far out, the image gets closer. If you bring the object closer, the image gets further away. So it works the opposite way around. So there is a certain point pretty much far out from the eye. Let's say something over here. I'm going to label this point as, let's say, n prime. There is a certain point over here that if no goggles or no spectacles are used, light rays from this point can actually be merged by the lens exactly onto the retina properly. So let me just, maybe I have to write this with a different color, maybe with red. So light rays are falling by, and from here light rays could actually meet onto the eye, which means this eye can see objects which is placed over here clearly, non-blurred image, and any object that is further down the line. Objects which are placed within this distance are not seen clearly. So the problem they're going to have is eating food. They cannot pick the bones of a fish, or they cannot differentiate between borboti and a morich. So it's pretty problematic. We don't want that to happen. So how can we take care of this problem? The solution is pretty simple. Opposite to the earlier case, we're going to introduce a converging lens in front of the eye, and this converging lens is going to cause the incident light rays coming from the near point. So let's say this is a converging lens. So these are the light rays which have come into the eye, and they're going to become slightly convergent before they reach the eye. And then that will make up for the additional recurrent convergence for the lens, and that will cause the light rays to once again fall onto the retina properly. So that's how we take care of long-sighted eye. Usually the way short-sighted eye and long-sighted eye problems can actually happen to people for a lot of different reasons, but myopia or short-sightedness is, as far as I understand, is pretty much hereditary. So if someone's parents have myopia, short-sightedness, their kids are more likely to have it. It's also something so similar to diabetes, although it's not always true. For example, both of my parents have glasses, but I don't. My sister don't, and my brother don't. So we don't use glasses, but both of my parents have glasses. But they picked my father has glasses for a very long time, but my mom got glasses when she was more than 40. So that can happen. And usually long-sightedness is an age-related problem. So when people grow old, then people can develop long-sightedness. Long-sightedness is not very common, but well, then again, people can have different type of diseases which can lead to this kind of problems. So that's for the whole eye scenario. Important information for to remember is that we are trying to make the light rays fall onto the retina, and we are doing the necessary job to or bring about the necessary equipment to make that happen. Any questions so far? Anyone?
No, sir.
We're gonna go for the prism. Prism is a pretty simple thing. Prism is basically defined as two. Let me just try to give a very simple definition of what a prism is. A transparent medium which has two faces that are not parallel to each other. Just that. A transparent medium which has two faces which are not parallel to each other. That's basically what you call a prism. Prism doesn't essentially have to be a triangle. It can be a trapezium as well. For example, you can have a prism that looks like this. You can also even have you can have a hexagonal transparent cup of water, which can also work as a prism for like here. So it doesn't have to be only a triangle. I mean, not essential to be triangle. As long as any transparent medium has two faces which are not parallel to each other, we can call it a prism. So that's that. Prism can do pretty interesting stuff. One of the important thing that Prism can do is that it can break down composite light, for example, white light, into its constituent colors. Isaac Newton did this experiment first, and he defined that those division had 7 colors in them. So we still learn them as 7 colors. That's the Gear sequence. But later it was found that if we want to define colors exclusively, we can do that by only 3 colors. RGB happens to be the first triplet. So red, green, blue was the first 3 exclusive color, which the mixture of these 3 core colors can give rise to any other color. And then the printing technology people, they came up with some other combination as well. Some people use CMY, cyan, magenta, and yellow. They use the mixture of these 3 colors for multiple other parts. So there can be a lot of different variation, but typically the whole spectrum can be divided into 3 core colors, and mix and match of these things in different percentages can give rise to all the other colors. There are a few things that you really need to understand for prism. Let me show you what is covered for your syllabus. First thing is that if you have a prism that is placed in this orientation, first thing first, I should have drawn equilateral triangle, but okay, no big deal. First thing, if light ray, I'm going to first do it for a single light ray. If a single light ray falls onto this surface at this angle, let's say this is the normal on the surface, so this is an incident angle. It is not, so this was supposed to be the original path of the light ray. It's not going to go in this path, it's going to bend closer to the normal. So let's say then the light ray bends closer to the normal and bends in this manner. As a result, it's going to fall onto the second surface with this much angle. This is the incident angle inside the glass, and it's about to go into air. So going from a denser into a rarer medium, or from a slower into a faster medium. So it's going to bend again. In this case, it's going to bend away from the normal. So have a look over here. This light is having 2 different bends at 2 surfaces. Whenever it is entering from air into glass, it is bending towards the normal. Whenever it is bending from glass into air, it is bending away from the normal, and together we're having a significant bending of the light. So this was the original direction of the light. Let me draw that with the red. This is the original direction of the incoming light ray, and this is the final leaving direction of the leaving light ray. So if we extend this angle backwards a little bit, we get an angle over here. This is the angle that we call angle of deflection. That actually how much bend did the prism cause in the path of the light. So that's what we mean by the angle of deflection. That what was the angle of deflection? It just so happens that these amounts of bending, I mean the amount of bending that we have over here, the amount of bending that we have over here, these amounts of bending are very much dependent on the speed of light. Because the way I have shown you earlier in earlier classes, that the refractive index in medium, let's say B, whenever the light is coming from medium A, is given by sine of angle A over sine of angle B equals to speed of medium A divided by speed of medium B. So the reason I'm writing this formula is to remind you that these angles this angle sine ratio are dependent to the directly proportional to their speeds. So different light rays, different color light rays will have different speed in the same medium. This is the part that I need you to understand clearly, that you have to understand this thing. C equals to F lambda. Within white light, so try to visualize white light like how can I say this? Try to consider white light like a rope where you have individual threads of fiber which are wound together. So together they make a rope. Whenever they pass through a prism, all of those individual strings they unwind and become separate of each other, something like that. And this frequency of individual thread or individual color of light, this is actually a key unchangeable property of any wave. I told you earlier that frequency of a certain wave exclusively depends on the source. Whenever a wave is released from a source, it cannot have its frequency changed. So, and within the vacuum or within air, vacuum and air are considered pretty much same, almost. Within the vacuum or within the air, all electromagnetic wave has the same speed, which is about 3 into 10 to the power 8 meter per second. It's actually a bit less than that. It's 2997 and 2458 meter per second, but approximately 3 into 10 to the power 8 meter per second works fine. So whenever the individual different frequency light rays enter from air into glass, they all have different amount of speed variation. All of them doesn't undergo the same amount of speed variation because the color violet will experience a different speed variation. The blue will experience a different speed variation because all of them has their individual different frequency and their speed would also be different. Frequency remains the same. So they have different lambdas. Individual for one single color, they have different lambdas, and so that essentially comes from different speed value. So in this case, for one single color, F is a constant and C and lambdas are directly proportional. So different color will have different speed, and that's why their change of speed will be different, and as a result their bending amount will be different. This is the physical reason that white light actually breaks down into its constituent colors. Now, the figure that I've drawn over here was for a monochromatic light. This is a keyword, and sometimes it actually shows up in the exam. Monochromatic basically means what it says in its name. It means a light of a single color. But the examiners would like to get write you a bit more specific answer. They appreciate the answer light of a single frequency, because monochromatic basically means light of a single color, which essentially comes from the physical property that there is no merging of multiple different colors, so there is merging of multiple different frequencies. One single frequency is what we're talking about here. That's that. Whenever we're going to introduce white light into a prism, then something will happen. So I'm going to draw right now a scenario for what's going to happen for a white light. So I'm going to draw this prism pretty large right now because I want all of you to see clearly what this figure is going to look like and not to make a mess whenever you're about to draw this in the exam. So I would like to have this on into shape. Oh, beautiful. Nice. Now, try to understand. Let's say I'm introducing white light onto this prism at this point coming from this line. So let's say this is my white light entering point. It's going to start to bend into all of its constituent colors right from this point as it travels from air into glass, and then it will go out in air again. So here's the deal. Try to observe. This was the original path of the light ray. I'm not drawing this. You shouldn't draw this in your actual exam, but I'm drawing this for your reference. So let's say this is the original incoming direction. From this point, light is going to divide into 7 different colors. All of those 7 colors are going to bend away from the normal. So bend towards the normal, because light is now traveling from a faster into a slower medium. All of those 7 light rays should bend closer to the normal. None of them should go further away. One of the really common mistake that the students sometimes do is that they do the spread in such a way that the light ray actually spread out in a haphazard pattern. That's something that you shouldn't do. Let me show you what is the correct version, and I'm going to show you what is the wrong version, so that you don't do that mistake. The correct version is draw one light ray like this, bending closer to the normal. Draw another one like that. This spread doesn't have to be really wide because you are not expected to draw 7 different rays over here. You just have to draw 2 of the marginal rays, and then you can just write up those names in the on the image, and that will be good. So you don't have to draw 7 different rays. So don't try to make it really far apart and mess this up. So that's one thing. Beyond this point, the light rays are going to fall over here, and from here they're going to bend further down. So now these light rays are going to go up because they're going to now bend away from the normal. So make this light ray bend down, and make this light ray bend even more down. So you can see there is a bit of a divergent pattern to it, because that's how this is going to work out, and that's how you draw. Now I'm going to show you the possible mistakes the students do, but before I do that, let me just complete the real. This is our screen, a piece of paper where the light rays are falling by. Now violet bends the most, red bends the least. I'm going to write this over here. For refraction, violet bends most. For diffraction, however, red spreads most. These two are opposite to each other. I'm going to explain what this thing is after a while. I'm just writing this down because I need to remind myself. So violet comes over the bottom side and R comes over here. If the question ever asks you to fill up a figure like this, it's always safe to write all the names in their actual words. If you don't have enough space over here, you can simply write the individual letter, just let's say V, G, R, and then somewhere over here you can write up all the names. Let's say V, violet, E, I, indigo, blue, like that. So this is how the character looks like. Obviously, don't forget to give the arrows, and you don't have to draw 7 different light rays, and you don't have to draw this light ray either. You don't have to draw this. What is the easiest way to draw this thing? In my opinion, the easiest way to draw this thing is that in the actual exam, you're going to be given this triangle, you're going to be given this incoming angle, and maybe they might give you the normal, they might not give you the normal. That can vary, and then they are asking you to complete the figure for the breakdown of the colors. How should you do that? Here's how should you do that. Take up the ruler. Rulerটা যেন কি দিয়ে ঘোরায়, কন্ট্রোল দিয়ে না,
scroll দিয়ে scroll দিয়ে
scroll দিয়ে, yes, thank you. So you hold up your ruler like that, and then you know that this is the alignment that you have, and just tilt your ruler a little bit while keeping this contact point over here. So keep your pencil right over here and tilt your ruler a little bit, drop your first ray, and then you tilt your ruler a little bit more, drop your second ray. So that way you know that you have bent both the rays towards the normal. Drop those 2 rays up to this point, and then hold up your ruler about this line a little bit, bend it a bit more. No. Yeah, bend it a bit more and draw up this one, and same thing, hold your ruler against this line, keep your pencil onto this dot, and bend your ruler a little bit closer away from the normal. Okay, away from the normal, and then you draw this one. So just simply hold your ruler and change it for every single surface point, and as a result you will be able to draw it much more easily. Here is a mistake that the students do. There are multiple different versions for it. I'm gonna show you another version of this figure where the light rays would not split at the first surface. If that's also a pretty common question, and students also sometimes mess it up. The common mistake that the students do is that in many cases they do not draw both of these light rays bend towards the normal. In many cases, they draw these light rays to spread around like that. So just like that, a very wide spread. And then these things are drawn pretty perfectly. So doing this is wrong. Don't do that. Be careful not to do that. And you don't have to draw 7 different lines. You don't have to draw 7 different lines. There is another variation to this. The other variation for this prism figure can be like this. In some cases, they can give you a light ray that looks like this. This much is given to you as a question, and they're asking you, this is a white light ray, complete the figure for the necessary breakdown of the light rays. So how do you do that? Can I make this thing any smaller? I don't want to make it small, I just wanted to make it thinner. I cannot make it thinner. Oh, beautiful. That's what I was looking for. So I had a reason to make this a bit thinner like that, because otherwise I wouldn't be able to accommodate all my light rays over here. So here's the thing that's going to happen. Whenever the light ray is going to fall on the first surface at 0° incident angle, because the light ray is perfectly making 90° with the first surface, you're not going to have split on the first surface. Try to have a look at the comparison between these two figures. In this figure, the incident ray was falling with some angle, with some incident angle with the first surface, with the normal. But in this second figure, the white light ray is falling vertically onto the first surface. So you're not going to have the split starting from the first surface. This ray is going to run as white light through the prism undivided. Then as it is about to come out from here, then the split will happen. Because now on the second surface, the incident angle is no longer 90°. The incident angle is no longer 90°. So now we're going to have a little bit of split. So because of that split, now all the light rays should bend out from the normal. Now this is why the figure can become a little bit tricky, because you should see, I mean, if I just hold up my ruler, this was your original alignment. Now you need to draw all of your light rays beyond this alignment, which means, let's say, if this was the line, this was your line, something. Wow. I could do that, but I can. Wow. Okay, so let's say this was your original line. Now you need to draw all of your bent light rays below this point. So it's pretty simple. Just hold up your ruler about this point, at this point, and rotate it a little bit. You know, have this alignment, just bend it a little bit. You don't have to draw this dotted line. I do this dotted line to make sense with you. So draw one light ray like this, and then bend it a little bit more. Draw the other one like that. I'm going to rub off this dotted line because you are not going to draw that. And make this thing like this. And let's say here we have a screen which is going to read "Live here" in this manner. Don't forget to give arrows. That's also another possibility. Sometimes figures can also show up upside down. Upside down as in situations like this. If figures are like this, white light comes in, then that breakdown might as well look like that. In which case, Vivgear is just going to be the opposite version. Violet would be them on the top. You just remember that violet bends the most. That is always easier to work by. Oh, why did the light bend when it entered the prism? For this one, or for the second figure, or for the first figure?
The first figure.
Because it is traveling from air into glass. I'm assuming that the prism is made up with glass. So there is a change of medium. It is moving from a faster medium into a slower medium. So That's why it actually changes the angle, because I wrote the equation over here to make sense with you that if
So not
it is
this one, the down below, the one below.
this one,
This is the second one. Yes.
okay, here it is not bending at all. This is going to be just continued as is. It's bending only at the second step because now it is leaving from the glass, entering into the air. So it has to bend away from the normal. Change of medium causes refraction. Simple. What you could say.
So I go good, then should the value.
Change of medium causes the refraction. So when the glass is leaving on the second surface, it is actually entering from inside the glass medium into the air medium. So medium change হচ্ছে তো. So যেহেতু medium change হচ্ছে, তাহলে obviously কি হবে? Refraction হবে. And because there is an incident angle over here, there will be measurable refraction angle. শুধুমাত্র জিরোর জন্য আমরা perfectly zero পাই। মানে when the light rays fall onto a surface vertically, it also enters the second surface vertically. That's an exclusive case. Apart from that, in all other cases where there is a measurable incident angle, there will always be measurable refraction angle as well.
But so when the white light entered the prism at exactly 90 degrees, why didn't it bend there?
Oh, why did it not bend?
Yes.
Because at 0 degree incident angle, we always get 0 degree in 0 degree angle, 0 degree refraction angle as well, because the light rays is not hitting this surface at any angle. I mean, it will slow down whenever the light ray travels from the air into the glass medium, entering at 90 degree. Then this light ray will be definitely slowed down significantly, but there would not be the spread or there wouldn't be an angle because they are all just going in the exact same direction. I could tell you that by mathematics, if this has to be zero, then this should be zero as well. But that mathematics actually doesn't stand out because 0 by 0 actually still gives you infinity. It doesn't give you actually any measurable sense. Or I could write it. How about I write it in this manner? In this manner, have a look. Sine of theta A should be equals to the effective index multiplied by sine of theta B. Let's say this is our equation. Okay. Now we know for a fact that n cannot be zero. That's a value of effective index for a denser medium. Can it be zero? Let's say for glass or water, it cannot be zero. So if this angle has to be zero, if the incident angle is zero, that necessarily means the total sine angle has to be zero as well. Doesn't that mean that the whole right side should also be zero? But on the right side, n cannot be zero, which necessarily leaves us the option that sine theta b must also be zero.
Yes, sir.
And for what theta value does the sine ratio become zero?
When theta is zero.
Does it make sense?
Yes, sir.
Beautiful. So that's why the light rays doesn't bend at the first surface when it is entering vertically into the surface, but whenever it's entering with an angle, it can bend. And if the figure is upside down, drawn in the reverted way, then the figure sequence will be reverted as well. The other thing that can happen in some of the cases is that if we have a 45-degree angle prism, which are more commonly used for binoculars and in periscopes, or also in long shot TV cameras, for example, sports cameras where you can actually see the whole zoom thing, bowling and so on, so cricket field match and so on and so forth. 45-degree prisms work in a very interesting way. Here's the deal. This is how a 45-degree prism looks like. I wanted it to be 45 degree. So this is how a 45-degree prism looks like. Basically, it's an isosceles where both of these angles are perfectly 45 degrees. The idea of 45-degree prism is that they work like a reflector, but much better than a mirror, because they are placed in the path of the light rays in such a way that light would enter into this surface perpendicular. They're gonna fall onto this tilted surface at an incident angle of perfectly 45 degree. Now you need to understand this. This is going to be 45 degree perfectly because this is 45 degree, this is supposed to be 45 degree, and this whole angle is 90 degrees. So this is going to be 45 degree as well. The material of this 45 degree glass prism is chosen in such a way that it has a critical angle that is significantly less than 45 degrees, maybe 40 degrees, 42 degrees, something like that. Which means whenever light rays would hit this surface, here is glass and here is air, Whenever the light hit this surface at an angle bigger than critical angle, no light will be left out onto the air. The entire light rays which is going to fall onto this surface is going to be 100% reflected back. That's why I use the term total internal reflection. No light passes out, no light gets absorbed either. So 100% light will be reflected back. And because it is a perfectly 45-degree prism, that reflection also is going to fall on the second surface at 90 degree as well. Sorry, 0 degree as well. 0 degree incident angles or 90 degree with the surface. And that's going to leave out vertically out as well. So this is also can happen for prism. The reason we prefer to use a prism other than using an actual physical mirror, because mirrors use, I mean, what is actually a mirror? A mirror is basically a transparent medium, for example, a piece of glass on which, behind which we have a layer of a shiny material, typically silver. And so that the silver material doesn't get oxidized, we usually apply another layer of ferric oxide, which gives it a bit of a brown tint. Ferric oxide layer is added in the back so that the silver doesn't get oxidized or doesn't get peeled off. So that's basically what a mirror is. That physical reflection process actually absorbs a significant amount of light, which doesn't happen if we use total internal reflection. You might wonder that when this light rays is actually transferring through the air into glass and then from glass into air, through this process of medium change, doesn't the light gets absorbed? The answer is yes, that light does get absorbed, but this process gives a far more brighter reflection compared to this thing. In all cases, no matter how well we make a mirror, a prism actually does the job with a far less manufacturing cost. So you can get more bright image with less manufacturing cost compared to a really well-engineered mirror. So that pretty much solves the problem for optical devices where we can get really beautiful images. So that's another case for prisms. So in this case, we are not dividing the light rays into 7 constituent colors for any purpose. We are simply using a perfectly 45-degree angle prism to work as an alternative for a mirror, and we are using total internal reflection because we want more bright images. Does it make sense?
Yes, sir.
Is there any other question that you would like to ask about the prism thing that you might have come across in your other sources of study, school or other places that you might want me to answer? If you have any, you can share.
Sir, do all the different colors have the same frequency?
No, no, all the different colors have different frequencies.
What do they have common in?
In vacuum, they all have the same speed. I'll help you. In vacuum, all of them have the same speed, 3 into 10 to the power 8 equals to individual frequency into individual lambda. So the one that has a big frequency is going to have a small lambda. For example, if you consider the whole visible spectrum, we have gamma, X-ray, UV, visible, IR, micro, and radio. This is the whole sequence of the electromagnetic spectrum. All of this this entire electromagnetic spectrum in vacuum, all of this wave has the same speed. This one has the highest frequency and smallest lambda. In such a way, if you measure both of these things and do a product of F into lambda in vacuum, you're going to get this number. Same thing for IR, same thing for radio waves. But radio is going to have a much smaller frequency and a really large lambda. But the product of these two things in vacuum is still going to give you 3 to the power 8. এটা আরেকটা জিনিস একটু পরে বলছি, এটা বুঝছো কিনা দেখো।
জি স্যার, বুঝেছি।
ঠিক আছে, এটা হচ্ছে ভ্যাকুয়ামে সবার স্পিড সেম। আর না ভ্যাকুয়াম যদি ফিক্স করে দিতাম তার মানে কি, এটা হচ্ছে একটা মিডিয়াম ডিপেন্ডেন্ট, মানে এই স্পিডটা হচ্ছে একটা মিডিয়াম ডিপেন্ডেন্ট প্রপার্টি। whenever we're going to transfer all of them into a different medium, all of them will experience a change of their speed, and in that process frequency will be the same. So এখন মনে করো, let's say I'm going to send in only violet color. মনে করো violet color এর frequency হচ্ছে, let's say ধরো violet color frequency হচ্ছে 15,000 hertz. I'm just coming up with a random number. This is not the actual frequency of violet color. Should I go 15,000 hertz? let me give a couple of more. Let's say violet color frequency is 1.5 in 10 to the power 6 hertz. Let's say this is the frequency of violet color. This frequency of violet color is an unchangeable property no matter where the violet color is, irrespective of medium. এটা ভ্যাকুয়ামে থাকলেও violet color frequency এটা এয়ারে থাকলেও তাই, গ্লাসে থাকলেও তাই, এয়ার ওয়াটারে থাকলেও তাই, অয়েলে থাকলেও তাই, গ্লিসারিনে থাকলেও তাই। violet কালারের যে প্রপার্টি সেটা প্রাইমারি ফিক্সই হবে হচ্ছে তার ফ্রিকোয়েন্সি দিয়ে। This frequency of electromagnetic wave is what we call violet color, period. এখন যখনই এই violet color একটা স্পেসিফিক ফ্রিকোয়েন্সি এক মিডিয়াম থেকে এক মিডিয়ামে যাবে তখন এর স্পিডটা চেঞ্জ হবে। So if you consider for a specific color, whenever we use the term v equals to f lambda, for a single color the f becomes a constant, and then the f and lambda becomes codependent on each other where v is proportional to lambda. So যে মিডিয়ামে স্পিড বেশি সেই মিডিয়ামে ল্যাম্ডা বেশি হবে, যে মিডিয়ামে স্পিড কম সেই মিডিয়ামে ল্যাম্ডা কম হবে। I'm getting my point. One single
Yes, sir.
color going in multiple different medium will maintain its frequency, but it will have different speed and different lambda proportional to each other. But whenever all the electromagnetic waves are considered to travel in vacuum, exclusively in vacuum, they are all going to have the same speed. This is not true for any other medium, by the way. Let's say if you send the entire electromagnetic spectrum through a different medium than vacuum, let's say glycerin, you're going to send the whole electromagnetic spectrum through glycerin. All the individual frequency components are going to give different speed. They're not going to have the same speed. They're going to have different speed in such a way that vacuum either individual frequency chilo, glycerin either individual frequency same থাকবে, but the speed টা change হবে and that is going to affect the lambda as well, or I could say the other way around, the lambda change হবে and that is going to affect the speed as well. Individual frequency values will always remain the same. তার মানে হচ্ছে যেই সোর্স থেকে তোমার গামা রেডিয়েশন বের হচ্ছে ওই সোর্স গ্লিসারিনের ভিতর গামা রেডিয়েশনই দিবে, ওই সোর্স ওয়াটারের ভিতর গামা রেডিয়েশনই দিবে, because that is dependent by the source and defined by the frequency property of the wave. But whenever that gamma radiation will travel through a vacuum, it will have a speed of 3 × 10⁸ meters per second. Whenever it will travel through water, it is going to have a much smaller speed than that, and the lambda will drop in the same ratio. Does that answer your question?
Yes, sir. So, sir, irrespective of the medium, the frequency always remains constant.
Yes, for a specific color, the frequency always remains constant irrespective of medium.
Yes, sir, got it.
Any further question, anyone?
So how can we change the frequency of a light wave?
আসিফ আর একটু জোরে বলতে হবে অথবা একটু কাছে এসে বলো বা মাইক্রোফোন কাছে নিয়ে বলো।
How do we actually change the frequency of a light wave?
I'll tell you what. We actually don't change the frequency of a light wave once it is actually created from the source. We can choose different sources to give us different type of light rays. For example, come to think about it, for example, let's say potassium permanganate. তোমরা কি chemistry potassium permanganate দেখছো? Have any of you seen?
Of course, see.
It's a bit purplish. Or if I want to give you another chemical that you have already seen that has a specific color other than white, what crystal color that do you know?
So chlorine is green. That one.
Gas is not green. Chlorine compounds look green. Chlorine is green. Chlorine green. I think chlorine was colorless. So chlorine might have been green. I'm not sure. My bad. Iodine is a bit brown. Okay, let's get that. Let's say iron. মরিচা কালার কি রকম? আমরা সবাই তো মরিচা দেখছি তাই না? মরিচা কালার হচ্ছে কি রকম? It's like a bit brownish, right? মাটির মতো, মাটি কালার. So that source, whenever white light falls onto it, it absorbs all the individual color and gives out a little bit fraction. Let's say if I write the VV or sequence, the rust moricha gives out a color that lies somewhere over here. Yellow এবং orange এর মাঝামাঝি একটা color সে emit করে. So if this is a piece of rust on a piece of iron or something, whenever we're going to send white light into this, it's going to absorb all the colors and only give out or only reflect this specific segment. So because it reflects on this part, that part is reflected off in all directions, and whatever that light is received by our eye, we see this object to be of that color. The reason rust looks of this color because it is typically getting white light delivered to it. But if we try to observe rust in a location where the source itself only gives blue light. So, for example, let's say you have a blue light source. If you wonder how do we make a blue light source, pretty simple. You have a white light source, and if you place a blue transparent polythene, or those things are called filters, you can place over here, and that filter can actually absorb all the other colors and only gonna let out blue out of it. And if you place a rusty piece over here, that thing is gonna appear to be almost black, because this thing is entirely capable to absorb all the blue part. You're not delivering it something to reflect, so you're only delivering something to absorb. So it's going to absorb all of that color and going to appear colorless / black. So the question that was that how do we change the color of something? We actually change the color of something by choosing a different material that is capable of give us a different color, or by feeding it a different color than was earlier. So yeah, does that answer your question?
Yes, sir.
বুঝা গেছে clearly?
Yes, sir. বুঝে গেছে।
Beautiful. I could actually show you one pretty interesting. So that's pretty much it for the optical chapter. I'd like to start on magnetism. I still have how much time? 23 minutes to go. Yeah, 23 minutes to go. I'll take a very small break. I'll be back in 3 to 4 minutes. I'll be right back.